if you stood on top of a nuke and blew it up just right, you could crash land on Mars after a few days, but only if you're indestructible. Otherwise, you're gonna need a rocket and plan an efficient trajectory across deep space using the knowledge of orbital mechanics. A subject that feels more like history than science. Right, it all started with Tycho Brahe, then Kepler, then Newton came along, Lagrange, don't forget Lagrange. Yet we all have to sit through it in order to begin thinking about navigating space. But what if I told you you can throw all of that away, start with a couple of equations, a computer and some common sense, and plan a mission to another planet like Mars? Let's start with the most basic concept, position. You have the same position as Earth, but want to have the same position as Mars. But the magic button that instantly changes your position sadly doesn't exist. Instead, we're going to have to cover that distance over a duration of time, just like this moving train. But since we can't just hop onto a moving train, it means we're going to have to increase our speed gradually, in this case using the thrust from a rocket engine. Let's say this rocket engine gives us a certain amount of thrust. You can divide the thrust by our total mass and get the acceleration. Our acceleration then continuously changes our velocity, which then continuously changes our position. Meaning that by controlling our thrust, we can start predicting where we're going to be and how fast we're going to go. Now let's increase our thrust even more. Aim our track straight at Mars. And once we're going fast enough, right, now that we're off the rail, we're going to have to predict where we're going to end up a lot more carefully. To do this, let's first simplify ourselves into a point that happens to be on the surface of the Earth. From here, we can figure out our exact position in 3D, starting by measuring the distance between the center of the Earth and ourselves along the X, Y, and Z directions. We can write the numbers down and keep track of it. And since we know the speed and angle we left the surface of the Earth from, we can split that onto the same 3 directions, and again write down their sizes. Now, every second, we can start feeding the velocity values into the position values. In effect, we're now simulating a straight line trajectory that heads towards Mars. But sadly, we all know that Earth has a gravity, which is governed through Newton's law of universal gravitation expressed through this equation. What it simply means is that we need to take our position, use it to calculate our acceleration, which then feeds into our velocity. So now when we run our simulation, we find out that we slow down and eventually fall back to Earth. To fix this, we can try going faster to escape Earth's gravity altogether, and aim a little higher to continue heading towards Mars. But can we actually make it to Mars using this trajectory? Well, zooming out again, we find out that Earth and Mars are moving at different speeds, and when we account for that, as well as the fact that the Sun has a gravity, we'll miss entirely with no way to correct for our mistake. So instead of trying to shoot a moving planet like Mars, let's try and shoot a stationary hot air balloon that's on Earth. In this scenario, we're simulating a cannon launching a grenade in such a way where once the timer runs out, the balloon will surely pop. Now, with gravity affecting the grenade's trajectory, we can aim just above the balloon and shoot extremely fast, but since we can miss early on, the grenade will pop far too late. On the other hand, we can aim almost straight up, but then the grenade will blow up far too early. This can only mean that there has to be an angle in between where the grenade will reach the balloon at the correct time to pop it successfully. And yes, you could find the formula for the correct speed and angle, but they're not really needed for this result since we can just aim higher to arrive slower or aim lower to arrive faster. This means that we can actually use this method to try and shoot ourselves all the way to Mars, this time accounting for the Sun's gravity. And we can start by aiming just above Mars and firing faster and faster until we get a lock on where Mars should be sometime in the future. We can even increase our angle and adjust our speed to see all the trajectory that could get us to Mars. Now, seeing where we'll end up in the same duration of time, we see that only one of those trajectories will get us to Mars. Again, there are formulas that help us describe this trajectory, but we don't really need them since we can use the method that we have. but is this the best trajectory we can find? Well, let's change things up a bit. First, we can shift our planned departure date, which will move Mars around relative to the Earth, as well as the arrival date, which will move Mars's final position to finally place it opposite of the Earth. This way, we can actually benefit from the Earth's velocity to push us forward, needing only 3 km per second of effort to get onto our desired trajectory. And when we arrive, we need to accelerate just a bit to match the speed of Mars. Now, by adding the delta V leaving Earth and arriving at Mars, we can get the estimated effort, or basically the cost of the mission. Now, to see this more clearly, we can calculate the delta V needed for each departure and arrival date pair and plot the result onto a 3-dimensional graph. And by looking at the bottom of the plot, we can again find that our opposite side strategy is the cheapest one available. In this case, we've actually rediscovered what's called the Hohmann transfer maneuver, which can be described using this equation as the most efficient method to travel from a smaller to a slightly larger orbit. But sadly, we cannot use this to travel between 2 planets for a couple of good reasons. The first is that it assumes that the Earth and Mars's orbit are both circular, which isn't true. The real deal breaker is when we find out that Mars's orbit is tilted by up to 2 degrees from that of the Earth's. So you could plan to arrive at the correct spot in 2D, but still be off by 7 million kilometers. In this case, we now need to search for a trajectory along this plane that is tilted relative to the plane of the Earth. And although the resulting initial velocity isn't too fast, since it's tilted up, we need to leave the Earth at a speed that is just way too high. But why can't we just find a trajectory that's on the plane similar to that of the Earth? Well, after trying a bunch of angles, you'll find out that the Sun's gravity will always bring your trajectory all the way back to the point opposite of the Earth, and if Mars is above that point, we'll have no choice but to arc over the Sun. To fix this, we need to try to avoid arriving on the opposite side of the Earth. One way is to depart late and arrive early, or depart early and arrive late. All of this is to try and benefit from the Earth's orbital velocity as much as we can. Now we can update the plot that we had using what we learned and see the 2 strategies separated by a gap. And since we also know where Earth and Mars was in the past, we can redraw the plot every 26 months when Earth passes by Mars, revealing an interesting pattern. And since we can predict the future, we can also draw them in that direction. In effect, this can also help us plan missions way ahead of time. Again, we've managed to rediscover something called the Porkchop plot, which is something we can use to not only plan missions between Earth and Mars, but also between any 2 planets in the solar system. Although people think they look like pork chops, I think they're more like butterflies to me. What do you think? Yeah, these things are pretty cool to look at all day, but let's actually use them to plan a real mission. Let's look at the transfer window of 2033. We can pick a comfortable spot in April, where we plan to leave Earth and travel for 200 days to arrive on Mars on this arcing trajectory. But how do we reach this trajectory all the way from Earth? In short, we have to leave the Earth at the correct speed and direction. But since Earth has a gravity, we need to first take a rocket into an orbit. But not just any orbit, it has to be in plane with the departure direction. This is so that when we reignite our engine in orbit, we can thrust forward to not only leave at the exactly correct speed, but also in the correct direction. Well, let's see what happens when we run our simulation forward, accounting for the gravity of Earth, Mars, and the Sun at all time. Well, in this case, we end up missing Mars by several 100,000 kilometers. Yeah, this is a pretty big error, so let's try and do some adjustment to try and close the gap. Now, by looking back at our ejection burn, we can adjust it left and right, up and down, as well as adding and subtracting to the burn itself. All of this is to try and adjust our future position in 3D, but how exactly do we do that precisely? Again, let's start with a simple simulation in 2D, where we place Earth and Mars fairly close to each other to simulate a fairly complex gravitational field. From here, we can pick a simple trajectory to get us close enough to Mars. But say we want to get to this exact spot, we can start varying the adjustment to our ejection burn to see where we can get by doing these adjustments. And by looking at the best result, we can see the combination of adjustments that will lead us to it. Now what's nice about this approach is that when we're close enough, we only need to run just 3 simulations and use that difference to chart out a grid, where again, you can project the target onto the axis of the grid to further improve your adjustment to any position that you like. Now, if you try to describe this method more mathematically into a formula, you can see that you can expand it into 3D, which in this case can help us to not only reach any spot around Mars to slow down and capture into an orbit, but also pinpoint the exact point and time to land on Mars. And of course, there can be mistakes that knock us off course, but we can also use the same mathematics to plan course correction maneuvers to put us back on track. So after months of traveling through space, you've managed to enter Mars's atmosphere and somehow land softly without dying. But sadly, you're going to be stranded here for at least 2 years until somebody can come pick you up. Anyways, now you have all the time in the world to study all of orbital mechanics, including how one orbit can be crazier than another, what a periapsis is and how 2 of them can argue, and maybe figure out how to come home. For now, please enjoy your time on Mars. Thank you so much for watching, subscribe if you like, and remember, don't explode.